Dear students, what is that you can see on this picture? Well, this is Hero's engine. It was designed by the engineer Hero of Alexandria in the 1st century AD. That is 2000 years back. Well, this Hero's engine is the first recorded steam engine and reaction turbine, and even today our rocket engines and our jet engines runs on the same principle. So let us try to understand this engine before understanding what is thermodynamics. Now, what this engine does is it converts the heat energy of this burning wood into kinetic energy. How? There is steam inside this vessel. As soon as the steam gets heated up, the steam it flows up through the pipes and it fills up the sphere, and then it comes throughout the nozzles as the pressure increases. As a result, what happens is that the sphere it rotates. Now, what has been done? That the heat energy was converted into kinetic energy, and it can be successfully taken into work. You simply use a shaft and you can rotate the shaft, and then you can use this kinetic energy to do any useful work. Now, the thermodynamics, understanding of thermodynamics starts from here, because basically, thermodynamics is nothing else. It is the study of science. And if I say it is basically how heat is converted into power. And we have been trying to study this subject for a very, very long time. And the Hero's engine is an example which was designed 2000 years back. So we have understood what exactly is thermodynamics. It is basically science of energy, and even if you go deeper inside, it simply means how can we convert heat into power. Having said that, these are the topics that you're going to cover up in this video. What are the different approaches to thermodynamics, the continuum concept, and thermodynamic systems, surroundings and boundaries, open, closed and isolated system, what are intensive, extensive and specific properties, thermodynamic equilibrium, state postulate, thermodynamic process, path and cycle. So let's start. Approaches to thermodynamics. Now, whenever we are studying thermodynamics, what we need is a system. Now, there are two ways you can study a system. The system will definitely have some matter, and matter will have molecules. So you can actually take a microscopic view. Microscopic view means you are studying the particles, the molecules, right, individually, how exactly they are behaving. This is known as the statistical approach or the microscopic approach. But this is not what we follow in engineering, right? In engineering, we follow the macroscopic approach. What does the macroscopic approach says? It says we consider the entire body as one system. We don't study the individual molecules, but we study the whole system as a whole. And this is also known as the classical approach. Now, as we keep on understanding this subject, you will more be able to understand what exactly do I mean by macroscopic and microscopic. So let us move forward. Now, to understand this concept of macroscopic once again, let me try to explain you what is continuum concept, right? In continuum concept, the matter is treated as continuous rather than discrete particles, molecules, right? So in the first example, you can see these are different molecules. We don't study the individual molecules because even if you study the individual molecules, you can see there is gaps between them, right? Let me say this is an tank which contains 1 mm of oxygen. It will contain around 3 into 10 to the power 6 molecules. So we don't study these molecules, right? As instead, what we will consider it as one whole system, right? We don't consider the gaps between the molecules. We consider the whole matter to be continuous. And why we do that? Because it makes our study, right, significantly simple, right? Later on, you will keep on understanding how it happens. Now, I'm talking about system a lot, right? I'm talking about we study the system as a whole. We don't study the particles. So what exactly is a system? Now, thermodynamics have a very different way of defining a system. Now, as you can see on the screen, there are many different particles, the yellow particles, blue particles, the black ones, the red ones, and there are so many different particles, right? I want to study only the blue particles. So what I'm going to do, if I want to study only the blue particles, I'm going to draw a boundary, right, around the blue particles. And this becomes what? This becomes my boundary. Everything that is inside my boundary is the system. And everything which is outside the boundary is the surrounding. Now, once I have defined the system, that is, I wanted to study the blue particles. So I've defined the system. Now it becomes very easy for me to concentrate on the blue particles. How are the blue particles behaving with the surrounding? Is there any mass transfer between the blue particles and the other particles, the system and the surrounding? Is there any heat transfer going on? Is there any work output? So it becomes very easy for me to concentrate my study on the blue particles, right? I'm not distracted. Now, having said that, what if I want to study only the yellow particles, right? I don't want to study the blue particles. Let me say I want to study I want to study the yellow particles. So what I can do is I can simply draw a boundary across the yellow particles. When I draw a boundary across the yellow particles, then this becomes on my boundary, right? And whatever is inside the boundary is my system where I'm going to concentrate my study on, and everything except for the system, it becomes a surrounding, right? So you can see the boundary can be imaginary, it can be real, right? We'll see later on, right? It can be movable, it can be fixed the way we want. Okay? Now, if you take the system and the surrounding together, we call it the universe. We call it the universe. If you take the system and the surrounding together, we call it the universe. So, system is the region or the matter chosen for study. The surroundings are everything outside the system, and boundary is the surface separating the system and the surrounding, right? It can be fixed, it can be movable, it can be real, or it can be imaginary, and we are going to see that. And finally, what is universe? Universe is the system, boundary, and surrounding taken together. Having said that, let us try to understand the turbojet engine, right? I'm not going to into detail, but suppose you want to study the turbojet engine, right? So what we can do is, if you want to study the whole of turbojet engine, we can simply draw a boundary across the turbojet engine. And this becomes whatever is inside the boundary is nothing else but your system. And everything except that becomes your surrounding. And this is your system, right? Now, suppose you don't want to study the whole of the turbojet engine. Instead, you want to just focus on the combustion chamber, right? So what you can do, we can draw an imaginary boundary across the combustion chamber. That becomes the boundary, and the combustion chamber becomes the system, right? And everything except the system becomes the surrounding. Now it becomes very easy for me to focus on the system, right? That is the combustion chamber. How much fuel is coming in? How much heat is going out? Right? What is the mass flow inside? What is the mass flow outside? Right? Is there any heat loss? Right? In the combustion chamber, everything my study becomes very, very easy. Right? So I hope you have understood what is the difference, what is the meaning of system, surrounding, and boundary, and everything taken together is known as the universe. Now, what are the different types of systems possible? The systems can be classified into three types: open system, closed system, and isolated system. What is the open system? As you can see, an open system is a system where mass can go in the system and mass can come out of the system. At the same time, energy can come out and energy can go in the system, right? So in an open system, the mass flow rate is not equal to zero and energy flow rate is also not equal to 0, right? Now, energy flow rate can be of two types. We will see it in later on. It can be heat transfer or it can be work transfer, right? We'll see that later on. But in open system, both mass flow rates and energy flows are allowed, right? Now, what is closed system? As you can see, the lead is there, right? Definitely you can understand that mass flow rate cannot happen here. In the closed system, mass flow rate is definitely 0. No mass can go inside, no mass can come out of the system. But what about energy? Energy can go in, energy can come out. So energy transfer is allowed in a closed system. Now, energy transfer can be of two types. As I said, it can be work transfer, it can be heat transfer. We'll understand what is work transfer and heat transfer later on. Having said that, mass transfer is 0, but energy transfer is not 0 in closed system. Having said that, if you block both mass transfer and energy transfer, it becomes an isolated system. If you block both mass transfer and energy transfer, it becomes an isolated system. Now, mass transfer is blocked because you can see the lid is on, right? Now, how to block the energy transfer? If you just put an insulation, right, around the system, insulation is something which does not allow heat transfer to happen. So you can say it is an isolated system, right? So no mass transfer, no heat transfer. So closed system is a system where energy transfer is allowed, but no mass transfer takes place. Open system is a system where both mass and energy transfers are allowed. An isolated system is a system where neither mass nor energy transfer is possible. Having said this, let us take the example of a closed system. So you can see this is a piston cylinder arrangement with some gas inside, trapped inside it, right? Now you'll see that this piston cylinder arrangement does not have any valve. There are no valves, right? So the gas inside the piston cylinder arrangement, it cannot go out. Neither can new gas come inside. So you can see the mass transfer is blocked. So mass transfer cannot take place. But as the construction material of the piston, say if it is made up of metal, right? So definitely heat transfer can go in. We can heat the gas inside. The gas inside can also cool down, right? So definitely heat transfer can take place. At that same time, you can see if you take out heat, what is going to happen? The gas will get compressed. As soon as the gas gets compressed, the piston is going to move up, right? Now you transfer heat into the system, right? That gas. So what is going to happen? The gas will expand, the temperature increases, the gas expands, and as soon as the gas expands, what is going to happen? The piston is going to come out. So you can see you can also move the piston, and as a result, what happens? You can actually create work, generate work, right? By just transferring energy, you are also creating work. So this is a very good example of a closed system where mass transfer is not allowed, but energy transfer in form of heat and work are possible. Having said that, this is an example of an open system. Mass can come in, right? It definitely has to come in, right? In form of air, in form of fuel in the combustion chamber, right? Mass can go out in form of combustion gases, right? At the same time, it will deliver work, right? In form of rotation of shaft, and definitely heat can also get lost into the surrounding. So this is a clear example of open system. Now, guys, can you tell me any example that you know of an isolated system? You can please type it in the chats for me to know if you really know it. Well, I'll give you a hint. It is available in the most of the kitchens. In winter, we use it to keep things warm, hot, and in summer, we used to keep things cold, right? Can you guess what exactly is the example? Not perfect example of an isolated system, but something very close to isolated system. Now, as we are talking about systems, one thing we have to understand is that whenever we want to study a system, we must assign some properties. Otherwise, what will you study, right? If you want to study a system, first thing that we have to do is assign some properties to the system, and then we study how these properties are changing when the system is interacting with the surrounding. So what are some of the common properties that we assign to system? They are the pressure of the system, right? What is the temperature of the system? What is the volume? What is the internal energy? What is the enthalpy? What is the entropy? Yes, we are going to understand this later on, but pressure, temperature, volume is something you understand. So we are going to define what is the pressure of the system, what is the temperature of the system, what is the volume of the system, and when you define the properties, right, of a system, they become the thermodynamic properties of that system. Now, if I talk about properties, we'll also have to understand that properties can be of two types, mainly of two types, right? Intensive properties and extensive properties. Let us try to understand intensive property and extensive property with the help of an example. Now, let me say I have a box which contains a gas. It could be any gas, might be nitrogen gas. Right? Now, let me say the mass of the gas is m, the volume of the gas is v. Let me say it has some internal energy E, U, the temperature of the gas is T, the pressure of the gas is P. So when you are going to study the system, definitely you'll have to fix these properties. Now let me say I divide this system into two equal parts, right? As you can see. Now what is going to happen to temperature? Will the temperature change? Will the temperature become T by 2, T by 2? No, the temperature will remain same. Even if you divide it, what will happen to pressure? Pressure will also remain same. But what will happen to mass? Definitely you can understand the mass will half if you're dividing it into two equal parts. What will happen to volume? Volume will also get halved. What will happen to energy? Right? If you talk about internal energy will also become half. So you see, there are some properties which does not depend on mass. When you divide it into two parts, it does not depend on the mass, but there are some properties which depends on mass. And this is exactly what intensive and extensive properties mean, right? So intensive properties are those properties which are independent of mass. Whenever you are trying to remember it, just try to see the in, right? Both have in. Intensive is independent of mass. Examples are temperature, pressure, density. Extensive properties, on the other hand, are dependent on mass. For example, volume, internal energy, enthalpy, entropy, all these are extensive properties. Now, whenever you have these extensive properties, if you fix these extensive properties, it becomes very difficult to study the system. Why? Because as soon as mass comes into the system, these properties are going to change, right? And that's why it becomes very difficult to study the behavior of the system. And that is why we define a third kind of properties which are known as specific properties. What are specific properties? Specific properties are those properties, means basically the extensive properties per unit mass. For example, what is specific volume? Volume divided by mass. And we represent it by small v. See, extensive properties you represent by capital letters, whereas the specific properties we represent by the small letters. Small u is equal to internal energy divided by mass. Specific enthalpy, small h, is equal to enthalpy of the system divided by the mass of the system. So whenever you are expressing the extensive properties on unit per unit mass basis, we call it specific properties. Having said that, let us try to understand that what is the meaning of the state and then what is equilibrium state. Now, you have a system, right? What is the system? Suppose I want to study the gas which is contained inside the cylinder. So I'm going to draw a boundary, right? So this becomes the system. I'm going to draw a boundary. This becomes my system, right? So to study the system, what you have to do, you have to first fix the properties, right? Let me say the system, the gas is at a temperature T, the pressure P, it has some internal energy, it has some enthalpy, right? It has some volume, this is the mass, right? Whenever you fix the properties, you say the given system is the particular state, right? This becomes the state of the system. You fix the properties. The system is at temperature T, pressure P, volume V, mass M. What happens? Now the state of the system is fixed. So the conditions of a system at a given time, we call it what? We call it the state of a system, right? Now, if these properties are not changing with time, if these properties are not changing with time, we say that the system is in equilibrium state, right? The system is in equilibrium. The system and surrounding are in equilibrium, right? We call it equilibrium state. Now, the problem is, how many properties do we really need to study? Do we need to fix, right? For the system to be in equilibrium, there are so many properties: pressure, temperature, volume, mass, density, enthalpy, entropy. Right? There's so many different properties. Do we need to fix all the properties to see if the system is in equilibrium? Here, the state postulate comes to our help, comes to our rescue. It says that you just need to fix two independent properties, two independent intensive properties. If you fix two independent intensive properties, you can say the system is in equilibrium state. You need not consider the rest of the properties. Okay, we understand what is intensive property, properties which are not dependent on mass, but what exactly do I mean by independent property? Let us try to understand this. The independent properties are those properties which are not dependent on each other. Now let us check, what about pressure and temperature? Are they dependent or independent? Now suppose you have a system, right, and which is at a temperature T. Right? Now you put in heat, and what you do is you increase the temperature of the system. Now what do you think will happen to the pressure of the system? When you increase the temperature of the system, the pressure of the system will also automatically increase. Why? Well, you can also see it in the form of the ideal gas equation, right? That is P is equal to rho RT. You can see if the temperature increases, the pressure also increases. So you see, pressure and temperature are not independent to each other. If one increases, the other increases. If one decreases, the other will also decrease. So you cannot consider pressure and temperature, right, to fix the state of a system. Let us understand it a little bit more. Let us assume this nitrogen, which is at a temperature of 25 degrees centigrade, right? Now, just by giving the pressure of nitrogen, you cannot fix, you don't know, you cannot fix the state of the equilibrium state of the system, right? What you'll have to fix is two independent. Now, temperature and volume are two independent properties. They are also intensive as well as they are independent of each other. Similarly, pressure and volume are also independent of each other, but you cannot take temperature and pressure because they are not independent, right? You can take pressure volume, you can take temperature volume. And that is why when you try to solve questions, you mostly see that temperature, volume, pressure, volume are there mentioned in the equation, but only temperature and pressure is not mentioned, right? Because you'll not be able to analyze the system properly. We have spoken about equilibrium of a system. Now let us try to understand this in detail. What do I mean by thermodynamic equilibrium? Now, if I say a system is in thermodynamic equilibrium, it has to be under four different types of equilibrium. It must be under mechanical equilibrium, it must be under thermal equilibrium, it must be under chemical equilibrium, it must be under phase equilibrium. Let us try to understand one by one. What do I mean by mechanical equilibrium? It means uniform pressure within the gas and between the gas and the surrounding. Within the gas, the pressure must be uniform everywhere. If it is P here, it should be P here. Everywhere, the pressure should be P. Otherwise, there will be internal disturbances within the gas itself. And the pressure should be same between the system and the surrounding also. Otherwise, you see, if the pressure of the surrounding is more than the gas, what is going to happen? The surrounding is going to push the piston inside because there is a pressure difference. And obviously, if the piston moves up, the system cannot be in equilibrium. So if there is no mechanical equilibrium, we cannot have thermodynamic equilibrium. Similarly, there must be thermal equilibrium. What is the meaning? Meaning means that uniform temperature. Now, temperature within the system should be same everywhere and also between system and the surrounding. What will happen if the system and surrounding temperatures are not same? There will be heat transfer either into the system or coming out of the system, and as a result the properties of the system will change, and if the properties are changing, we cannot say they are in equilibrium. Similarly, we must have chemical equilibrium, which means there should not be any chemical reactions going inside the system, and also there should be phase equilibrium, which means that there should be a constant phase within the system. What do I mean by constant phase? Phases, what there are generally three types of phases which we study, right? Liquid, vapor, and solid, right? So whatever the composition, right? It need not be in one phase, single phase. It might be a combination of liquid and vapor, or might be all three, as in case of a triple point. But this should be in equilibrium, means there should not be any changes in the mass of a particular state. Well, you'll understand phase equilibrium later on when you study thermodynamics in much detail. Now, what happens if the equilibrium of a system changes? Now let me consider this piston cylinder arrangement. Let me say the system, the piston was initially at this position. When the system was at this position, the entire cylinder was occupied by the gas, right? Let me say this is the state 1, which is nothing else but the initial state. This is nothing else but the initial state. So initially the piston was here. The volume of the system was V1 and the pressure of the system was at this point of time, let me say P1. Then we apply some force or whatever happens, right? The piston moves from this position to this position, from 1 to 2. So the volume decreases to V2, and as the volume decreases, what happens to pressure? The pressure increases to P2, right? And the system moves from initial state to the final state, right? So this was the initial equilibrium state. This was also in equilibrium, and this is the final equilibrium state. So the system, it moved from initial equilibrium state of 1 to final equilibrium state of 2. And whenever this happens, we say a thermodynamic process has taken place. So whenever a system moves from one equilibrium state to another equilibrium state, we say a thermodynamic process has taken place. And in between, you can imagine that the system will attain many different equilibrium states in between, right? And if you join all those points, right, we say this as the path followed. The path which the system follows while traveling from 1 to 2 is nothing else but the thermodynamic path. So any change from one equilibrium to another equilibrium is called process, and the intermediate states the system passes through is the path. And if the initial and the final states are same, for example, suppose the body, it goes from say 1 to 2, the system, it goes from 1 to 2, and then say from it returns from 2 to 1. So you can see the initial state and the final states are same. This is the 1 is the initial state and 1 itself is the final state. We say a cycle. We say this as a thermodynamic cycle. Let us take the example of thermodynamic cycle once again. So you can see initially the system was here at point 1, right? It was the equilibrium state 1, right? It moved to the equilibrium state 2, right? The compression reduces the volume and increases the pressure. And then say from 2, again it moves back to 1, right? So it returns to its original condition. Then we say a thermodynamic cycle has taken place from 1 to 2, then 2 to 1. Having said that, what are the different thermodynamic processes possible? So there are basically 5 thermodynamic processes which you generally have, and in all the processes we keep one of the properties constant. We'll talk about it later on. It makes our analysis of a system easy. So if the temperature is constant, we call it isothermal process. If the temperature is constant, we call it isothermal process. If the pressure is constant, we call it isobaric process. If the volume is constant, we call it isochoric process. If the entropy is constant, we call it isentropic process. Yes, we are going to understand what is entropy and enthalpy later on, but let us just let us just learn the terms first, right? We are going to understand it in detail. And if the enthalpy is constant, we call it isenthalpic process. And if none of these properties are constant, right? If it follows something else, then we call the process polytropic process. If all these processes are not being followed. So having said that, this was the introduction to thermodynamics in 30 minutes. Please let me know the things that you liked about this and the things that can be improved in this so that it could be of better use to all of you. Thank you.